home stretch. We're in part 5 of our mock diploma exam, starting on page 24, and it's multiple choice question number 34. There's this reaction taking place here. It's a fusion reaction. We know that because two lighter things become one heavier thing. Notice, though, it's a little bit different than the one that we typically see. Usually it's H2 plus H2. Here it's H2 plus H3. Not a big deal. Okay, it's still two lighter becoming one heavier. Okay, it's still fusion. Neutron produced, energy released. We got a diagram there with an intermediate thing, right? We got the deuterium and tritium combining right here. And then we got this alpha particle and the neutron produced right here, but there's something in between here. Okay, there's something in between right here. Okay, that's not listed in the actual equation there. That's okay. That's okay. If we need that, we'll deal with that. Energy is released in this nuclear fusion reaction because why? Energy released in a nuclear reaction, it comes down to a two-word answer. What is it? Mass defect. And the mass defect is the difference in mass between the mass of what we start with and what we finish with. The answer is going to be D for that one, right? The mass of what we finish with is less than the mass of what we start with. Mass defect. Ten. I kind of like this question, actually. Kind of like this question. At a particular instant, the electrostatic force that the deuterium ion exerts on the tritium ion is 23.3 newtons. Here's the force. What's the distance between them? So we're going to say the equation we're going to use here is F is equal to KQ1 Q2 over R squared. That's the force between two charges. We've got to find R. Problem is we don't know what Q is, right? We know what F is. That's good. We know what K is. What's Q1 and Q2? Listen, guys. Deuterium is 21H. Tritium is 31H. They both have one proton. They're nuclei. They have no electrons. This is the one proton. The charge of this one is 1.6 times 10 to the minus 19. And the charge of this one is 1.6 times 10 to the minus 19. The number of neutrons is irrelevant there, right? The only thing that matters is the number of protons. So now we got the charge of this and the charge of this, both 1.6, because we're looking at hydrogen nuclei, whatever the isotope is. Rearrange this equation. R squared is equal to KQ1, Q2. Take the F down by dividing. Right? R went up, F went down. And then we're going to square root that. Do our math. And it works out to be 3.14 times 10 to the minus 15 meters, which, hey, pay attention to this one. They only want me to express the base on this one, right? Blank times 10 to the negative W. It's 3.14. It's not the W. We don't want the exponent there. We don't want the 15 there. $35. Boy, are we on the home stretch now, guys. Almost done. Almost finished here. 35. More information, additional information. How many times have we seen that today? We got this positive charge entering a magnetic field that's directed out of the page. It's the direction of the force. Right hand, thumb in the direction of the particle. Fingers out of the page. Thumb, fingers, palm points down the page, toward the bottom of the page. D. Hey, we got to get that question right. If we see that on the exam, we got to get that. We're going to see a number of challenging questions. Okay, we're going to see questions that are easy like this. They're not easy if you don't know your stuff, but we've got to be able to get these. Okay? Because there's going to be some that are too hard for us to get, right? So let's get the easy ones. 36. The neutron produced in the fusion reaction escapes the magnetic confinement because, well, neutral particles aren't affected by magnetic fields. Goes back to the information back on page 24 that talks about magnetic confinement. Okay, magnetic field, neutrons aren't Neutrons aren't affected by magnetic fields because they're neutral. Moving charges are affected by magnetic fields, not neutral charges. 37. Particular neutron traveling at that speed hits lithium and stops. Impulse. Hey, I'll tell you what. My gut feeling when I read this, just the first part of the first sentence there, conservation of energy. How come? Hey, if that's your first thought, that's good. I want that to be your first thought in that question. Why would I automatically think conservation of energy there? Charged particle slows down, right? That's what we think when a charged particle slows down. Now, it doesn't mean that 100% of the time that's what we're going to do, but at least it's valid every single time. Now, clearly they're asking us for impulse here, so we're not going to do that this time. We're going to do impulse here. The mass here is, what do you got here? The mass of a neutron is on your data sheet, 1.67 times 10 to the minus 27. And the change in velocity would be, the final is 0. The initial is, now we're told somewhere it's 5 point, yeah, in the question right here, it's the stem of the question, 5.21 times 10 to the 6. That works out to be negative 8.70 times 10 to the minus 21. Hey, A or B, how do you know it's elastic or inelastic? Listen, collisions are almost always going to be inelastic, right? If you got to guess inelastic, for sure, right? No, in fact, it says it hits the lithium blanket and stops. That's what tells us for sure that it's inelastic, right? Okay. But tell you there, if you got to guess inelastic, for sure. You guess on this one, you're going to guess right. But in the end, we know that it is inelastic because that particle stops. You can't conserve energy when it stops. Sorry, you can't conserve kinetic energy when it stops. Which of the following equations most likely describes a neutron-lithium collision? This one's kind of tough, actually. This one's kind of tough. Hey, tell me which two right now you can eliminate. Tell me which two you can scratch off right away. C and D, how come? Because those are neutrons. 0, 1, that's a positron. 1, 1, that's a proton. They're not neutrons. They have the neutron symbol, but the numbers are wrong. So it's got to be either A or B. Which one works? Let's balance them out and see which one fits. 1 plus 7 is 8. 0 plus 3 is 3. That seems to work. 1 plus 4 is 5. 0 plus 3 is, oh, wait, that seems to work as well. Not a big fan of this question, I'll be honest with you, because when I saw this for the first time, I expected one of them to balance and the other one not to balance. They're both possible. They're both conceivable, right? Why is the first one more likely? And that's what we're being asked for. Here's the most likely one. You're not going to get an atom. You're not going to get a nucleus with 3 protons and 1 neutron. It's just not going to happen. Okay? They're always going to be more closely balanced or more neutrons than protons. Okay? This would be, remember we talked about nuclear decay and you can have too many protons? This would be way too many protons compared to the number of neutrons. This one would. So our answer is A. But you know what? That's a tough one. Okay, that's a tough one to decide between A and B for sure. Last page. Oh, last page, last day of class. Both of these questions, right? To study subatomic structure, high energy particle accelerators are required because plasma, what? It's not the answer. If you're saying plasma, what? Then it's not the answer. Okay? Antimatter exists at high energy? What does that have to do with anything? The strength of the electrostatic force, the strength of the strong nuclear force. Both of those sound pretty good. Here's the deal, though. Not C. We don't need to blow apart the strong the electrostatic force because that's what already pushes things apart. Right? That helps us. That helps us to split things up. Okay, it's the strong nuclear force that we care about here. That's the attractive force, right? This is repulsive in the nucleus. It can be attractive in other places, but repulsive in the nucleus. This is attractive. So this is what we got to blow apart. And finally, which of the following decay equations describes beta positive? Well, it's going to be B or D, right? Because A and C have beta negative particles, electrons. Hey, look, we don't even have to know anything about quarks. Would you look at that? Beta positive has to have a neutrino, not an antineutrino. So it's got to be D. Let's just go through the quarks there just to make sure. Up, up, down. On your data sheet, you can find that up is 2/3, negative 1/3 gives me 1. Up is 2/3, negative 1/3, negative 1/3 gives me 0. So we got 1 goes to 0 plus a positron. What is that? That's a proton. Goes to a neutron plus positron, right?